Hello everyone, welcome to this lecture in the Neural Networks from Scratch series. This is another lecture on the topic of backpropagation. In the previous lectures, we have looked at backpropagating through a layer and especially the weights and the biases of different layers. And in the last lecture, we also looked at backpropagating through the loss function, or essentially finding the derivatives of the loss function with respect to its inputs such as a1, a2, and a3. So now we have developed most of the building blocks necessary to backpropagate through an entire neural network. If you look at any layer, we are now equipped to find the loss with respect to the weights of that layer as well as the inputs of that layer. We are equipped to find the derivative of the loss with respect to its inputs a1, a2, and a3. We also looked at how to find the backpropagation with respect to the ReLU activation class. The only thing which is now remaining is to find the derivatives of the output of the softmax function with respect to the inputs of the softmax function. Remember that before the outputs go into the loss, they are passed through the softmax activation function. Now, to find these partial derivatives, it's actually very tricky because if you look at a1, it depends on z1, z2, and z3, all of them like this. So a1 is actually e raised to z1 divided by e raised to z1 plus e raised to z2 plus e raised to z3. So the thing is, a1 actually depends on partial derivatives, or a1 actually depends on z1, z2, and z3, all of them. So it is not just enough to find the partial derivative of a1 with respect to z1. We actually have to find the partial derivatives of a1 with respect to z2 and a1 with respect to z3 as well. So let me show it with a different color. So a1 with respect to z1, z2, and z3. Similarly, a2 also depends on z1, z2, and z3. So it's not enough to just find the partial derivative of a2 with respect to z2. We need to find the partial derivative of a2 with respect to z1, z2, and z3, and similarly for a3. So for any given input data, there is actually a matrix of derivative values. When we look at finding the partial derivative of a1 with respect to, or partial derivative of the softmax output with respect to softmax input, and that gets a bit complicated, right? So keep that in mind and let's start this lecture. So now we have actually mastered everything before this final set of neurons, right? Before this final set of neurons, all we have is previous layers and inputs, and we have already discussed how to find the partial derivative of loss with respect to the weights and the inputs, right? Now actually what we need is we need the partial derivative of L with respect to z1, z2, and z3, and there are two ways to calculate this. The first way to find the partial derivative of L with respect to z1 is using the chain rule. It's the product of partial derivative of L with respect to a1 multiplied by the partial derivative of a1 with respect to z1. Let's look at the first term here. In the previous lecture, we actually looked at finding the partial derivative of the categorical cross entropy loss. And it's pretty simple. It's just the negative of the ground truth vector divided by the vector of predicted values. If you have not seen this lecture, I highly encourage you to go through it. So finding the first term is actually pretty simple. The second term is partial derivative of a1 with respect to z1, or rather the partial derivative of the softmax output with respect to the softmax input. And it turns out that this is actually very complex because, as I explained, a1 depends on z1, z2, and z3. So there is a matrix which comes in, and since we have a batch of inputs, it's a vector of matrices. So then it just becomes very difficult. It's possible to do this. So if you look at the mathematical derivation of the softmax activation function, calculating it takes a lot of time, and ultimately we have something called as the Jacobian of the matrix, which needs to be taken into the picture. So I'm not going into it in a lot of detail because I think this will be a distraction to this course. I'll upload the notes for those of you who are mathematically curious to explore option 1 further. But to all those who find this mathematically hard, and it is mathematically challenging, Don't worry, because we have a second option to find the partial derivative of loss with respect to z1, z2, and z3. And it turns out that this is actually quite an easy formula, so we don't have to go through both of these steps. Or the other way to do it is that if you mathematically write partial derivative of L with respect to a1, and you multiply it by partial derivative of a1 with respect to z1, the resulting mathematical formula is much simpler than the partial derivative of a1 with respect to z1. So rather than knowing about the mathematical details behind this operation, the partial derivative of a1 with respect to z1, I'll rather just tell you directly how to find the partial derivative of L with respect to z1, z2, and z3. So directly we are going to find the partial derivative of L with respect to z1, z2, and z3. We are going to bypass these two set of chain rule operations. And I'm going to show you the mathematical formula. It turns out it's as easy as the predicted values minus the ground truth. That's it. And let me show you the derivation for this very quickly. So here is how the derivation of this actually looks like. Partial derivative of loss directly with the z. It turns out it's the predicted value minus the actual value. So when you write down the entire mathematical operation, several terms cancel out with each other, and ultimately we just end up with these two terms, which is the predicted value minus the actual value. Don't worry about these mathematics. I'll be sharing this information in the description. For now, all you need to remember is that the formula for finding the partial derivatives of the loss with respect to z is just predicted minus the ground truth. Now, let me show you how it actually works in practice. Let's say we have three batches of input data. The first batch consists of, let's say, two inputs. The second batch consists of two inputs, and the third batch consists of two inputs. In each batch of input data, there are three output neurons, and their outputs are Z1, Z2, and Z3, which eventually pass through the softmax activation function. And These are the outputs of the softmax: point 0.7, point 0.1, point 0.2. Uh, Let me see. So yeah, the output of the softmax is point 0.7, point 0.1, point 0.2 point for the first batch. For the second batch, the output of the softmax are point 0.1, point 0.5, and point 0.4. And for the third batch, the output of the softmax are 0.02, point 0.9, and 0.08. So these are the predicted values, and the predicted values can be written in terms of the matrix like this. So remember, the first row here is the predictions from the first neuron, or the first batch of data rather. The first row is the prediction from the first batch. The second row is the prediction from the second batch, which I have written as the second column over here. And the third row here is the prediction of from the third batch, which I have written as the third column over here. So the predicted matrix can look like this. Now let's look at the ground truth. So in the formula, we have calculated the first term here. But now let's look at the second term, which is actually the ground truth. So let's look at the ground truth for the first input batch. So for the first input batch, the true value is 0. For the second input batch, the true value is 1. And for the third input batch, the true value is 1. So what does this mean? This means that for the first input batch, the first neuron is activated. So if there are three classes of the output, red, green, and blue, the answer is the first class. That's what this 0 means. True value equal to 1 means that the answer is equal to the second class, and true value equal to 1 again means that the answer is equal to the second class. So for the first batch of input, the true value is the first class. For the second class of input, the true value is the second class, and for the third batch of input, the true value is the second class. This can also be written in a one hot encoding manner. So if the true value is the class number 1, then the one hot encoding of this is 1, 0, and 0. If the true value is class number 2, then the one hot encoding is 0, 1, and 0. And if the true value, let's say, of the third batch is 1, then which means the second class. So the one hot encoding is again 0, 1, and 0. So then the ground truth can actually be written as again a matrix. So for the first batch, the answer is 100, which is the first class. For the second batch, the answer is 0, 1, and 0, which is again the second class. And for the third batch, the answer is 0, 1, and 0, which is again the second class. So what this formula actually tells us is to find the partial derivative of the loss which comes after all of these. That's the cross entropy loss. To find the partial derivative of loss with respect to z1, z2, and z3, all we need to do is take the difference of these two matrices. So what we will do is the subtract the ground truth, which is the second matrix, from the first matrix. And when you do this subtraction, you will get the answer like this. One easy way to look at the subtraction is that you look at the predicted matrix, and for the first row you look at which class is correct. So the first class is correct, right? So you just subtract the first element by 1. So the answer for the first row is minus zero point 0.3, and the other two elements remain the same. For the second row, which is the second batch of the input data, the correct answer is the second class, right? Which is the second index. So you just subtract the second index of the second batch by 1. Both other indices actually remain the same. So then the second index will be subtracted by 1, which is minus zero point 0.5. Both other indexes remain the same. In the third batch, again the correct answer is the second class, which is the second index. So then what you will do is that the second index of the third row will be subtracted by 1. The first index value and the third index value of the third batch will remain the same. So then the this will be minus zero point 0.1, and then the first value and the third value will remain the same. So then the answer is predicted minus ground truth, which is given by this matrix over here. And remember, like we did in the last time, when we actually implement the code, we will not stop at this answer. We will actually normalize it with the number of samples. So the number of samples here is 3, right? Because the output can either be from red, green, or blue. So we are going to, or rather, we have 3 batches of input data. So that's why the number of samples is 3. So since we have 3 batches of input data, we are going to divide every number in our output with 3. So then this will be the final output. So this is the gradient of the loss with respect to the softmax inputs. So this matrix which we calculated over here, which I am now noting with this star here, that is actually the partial derivative of the loss with respect to the inputs z1, z2, and z3. It's as easy as this to find uh, this partial derivative. Now that we have this derivative, we actually have all the ammunition to find the partial derivative of the loss with respect to every single parameter in this neural network. Because once we have the partial derivative of loss with respect to z1, z2, and z3, all we have is the layers preceding that, and they have the ReLU activation. So we have seen how to backpropagate through ReLU, and the layers have weights and biases and inputs as parameters, and we have seen how to find the partial derivative of loss with respect to all of those parameters already. So now what I'll be doing is that I'll be taking you through a code in which we'll first define a class which essentially is the forward pass through the loss, and then we also define a backward method in the same class. What that backward method will do is that it will directly calculate the partial derivative of L with respect to z1, z2, and z3 by using this formula, predicted minus the ground truth. So let's go to the code now. Okay, so I'm just going to zoom in a bit here to show you the different details. So I have titled this section as softmax classifier, combined softmax activation, and cross entropy loss for a faster backward step. So actually it turns out that if you multiply these two operations and calculate both of them separately, mathematically it takes a lot more time rather than just using a simple formula. So that's another reason why in practice we use this formula, predicted minus the ground truth. So I define a class which is called as activation softmax loss categorical entropy. The reason we have defined this class like this is because it combines the softmax along with the loss. So we don't have to define separate classes like this. So let's see what's happening in the forward pass. In the forward pass, what we are doing is actually we are calculating the softmax output. and then what we are doing is we are returning the loss. So that's the forward pass. And how the softmax output is calculated is the activation softmax, which is the class which we have already defined earlier, and the categorical cross entropy loss. So what's happening in the forward pass is that we are just looking at this network here. We are calculating, so if the input to the softmax is given, we are calculating the output of the softmax, and then we are calculating the categorical cross entropy loss from this output. And that's what is happening in the forward pass. The main purpose of this lecture, however, is to show you this backward pass which I'm going to implement. So, in these 4 to 5 lines of code, what we are going to do is that we are going to return the partial derivative of loss with respect to the softmax inputs Z1, Z2, and Z3 using this formula predicted minus ground truth. So, let's see how that is actually done. So, first thing what we do is that we look at the shape of the Y true, right? Remember that for the purposes of this code, it's actually good for us if the shape of y true is in the format of numbers like this. So like 0, 1, and 1. This was the shape of y true, right, which we looked at in the example. So what has been done here is that if the shape of the y true and the length is equal to 2, which means that if the y true is actually one hot encoded, so if the y true values are one hot encoded like this, we actually convert it into number format. So for example, if the input, the y true is 100, 010, and 010, we convert it into 0, 1, and 1. I'll show you in a minute why we do this, but it helps to write our code if we convert the one hot encoding into this number representation like this. Why is 100 equal to 0? Because it's the first class. Why is 010 equal to 1? Because it is the second class. And why is 010 equal to 1? Because it's the second class. If one label was 0, 0, and 1, then its true label would be 2. So remember, the true value index starts from 0. So that's what we are doing in this part of the code. If the labels are one hot encoded, we actually turn them into discrete values. Next thing what we are going to do is, this is going to be our output self.d inputs, and first we initiate the output to d values. Remember, the d values are the predicted values. So what we are going to do first is that, let's say we take our example, this example itself. First, what I'm going to say is that my output, this is my output. Initially what I'm going to say is that this is my output. Okay. uh, and then what I'm going to do is that I'm going to subtract 1 from appropriate indices. So let's say if this is the output, then what we are going to do is that we are going to do this operation. So let's look at this indexes. For example, the first index here is the range of samples. So if the number of samples is equal to 3, which is calculated here, the range will go from 0, 1, and 2. And the second is equal to y true. So let's take our example itself in consideration, and remember that the y true values are 0, comma 1, comma 1. So these are 0, comma 1, comma 1. These are the y true values, and I am also going to write the first set, which is the range of samples. So the range of samples is actually going to be range of 3, right? Because we have 3 batches. So the range of samples is 0, comma 1, comma 2. Remember, in Python, range of 3 will be 0, 1, and 2. So we will use these as, so this is the first index and this is the second index, right? So what has been written in this code is that, wherever you get the first index and the second index, you subtract that value by 1. So let me tell you what that means. So let's combine these initially. So 0 and 0. So what is the index which corresponds to the 0th row and the 0th column? It's the first one, right? So we'll subtract it by 1, which we have done over here. Then we combine the second two entries, which is the first row and the first column, which is this one over here. Then that will be subtracted by 1, which is the true answer. And then we look at the third pair, which is 2 and 1, which is second row and first column. So second row and first column, which means zero point 0.9. So then that will be subtracted by 1. So then here it will be minus zero point 0.1. All other entries will essentially remain the same. And this is exactly what is done in this part. So, if I were to say this in English, what's happening in this part is that wherever the true class is there, that particular value is subtracted by 1. For example, in the first row, the true class value is the first class, so that is subtracted by 1. In the second row, the true class value is the second class, so this second entry is subtracted by 1. And in the third row, the true class value is the second class again, so again the second entry is subtracted by 1. So this is what is mathematically happening, and the best way to represent it in code format is to index the self.d inputs, and the first part of this index is range of samples, which is 0, 1, and true. And why true in this case is 0, 1, and 1. Then what we do is that we pair them up. So 0 and 0, which is 0th row and 0th column, will subtract 1. First row and first column will subtract 1, and second row and second column will subtract 1. And that's the resulting answer. But there is one more step, as we saw before. We have to normalize with the number of samples. So we have to divide everything by 3, because number of samples are 3. And that is exactly what is done here. So in the last portion of the code, whatever output we have, we divide everything by the number of samples. And as I explained to you before, the reason this is done is so that the gradients do not increase to very high values. Remember, when we do gradient descent later, all the gradients from all the batches will accumulate. So if we don't normalize, the gradients will become very large and convergence will be difficult. uh, that's why it is very essential to normalize with the number of samples. So this is the code for the backward pass. We'll now actually see how this works in action. So what I'm going to do now is I'm going to take a softmax outputs. So here we can see that the softmax outputs, which are essentially um, so the softmax outputs are these values which I've shown here in this whiteboard. So it has these three sets of values. So for the first batch of input, the softmax output is this. For the second batch of input, the softmax output is this. And for the third batch of input, the softmax output is this. And the class targets are 0, 1, and 1, which is the same case what we considered. Now what I'm going to do is, first I'm going to initiate an instance of this class, which is activation softmax loss categorical cross entropy. So I create an instance of this class which is called as softmax loss, and then what I will do is I will call the backward method. And remember, the backward method which we have described here takes two arguments. The first is d values, which are the predicted values, which are the softmax outputs, and then it takes the true values, which are the class targets. Remember, the class targets in this case are already discrete. They are 0, 1, and 1. So let me mark them here. So the class targets are already discrete, 0, 1, and 1. So this part of the code won't be invoked, because the if we calculate the length, it will be equal to 1. This part of the code is only invoked when we have the class targets as one hot encoding. So then we call this method softmax loss.backward, and which takes two arguments. It takes the softmax outputs as the first argument and the class targets as the second argument. And then that's it. And then we return softmax loss dot d inputs, because our output is stored in this variable called d inputs, as we saw over here. So then finally, when we take this output, we will be printing the gradients of the combined loss and activation function, and these are the gradients. So let's actually see whether these are the same values which we obtained over here. So let's look at the values which we obtained. So for the first row, which is for the first batch of input data, the values which we obtained are minus zero point 0.3 by 3, which is minus zero point 0.1. This will be 0.033, and this will be 0.066. So if you look at the code, The first row is minus zero point 0.1, 0.033, and 0.066. This is exactly what we obtained. If you look at the second row, the answer is 0.033 minus 0.167 and 0.133. So if you look at the second row, it will be 0.033 minus 0.167 and 0.133. It's exactly what we had obtained on our whiteboard calculation. And if we look at the third row, the answer is 0.0066 minus 0.033 and 0.0266. So now let's compare it with the third row over here, which is 0.0066 minus 0.033 and 0.0266, which is exactly what we had obtained on the whiteboard. So our answer from the code and our answer from the whiteboard approach is exactly the same. So that brings us to the end of this lecture, where we calculated the partial derivatives of the loss directly with the softmax input using a simple formula predicted minus ground truth. As I said before, now we are completely ready to write the entire code from scratch for backpropagation and chain the different modules together. So the hard work which we have put in for the past 4 to 5 lectures in calculating the gradient of everything, gradient of the loss function with respect to the weights, gradient of the loss function with respect to inputs, gradient of the loss with respect to the ReLU, gradient of the loss with respect to the inputs to the softmax. We have all of these things which we have added as a method called backward when we define the layers and also when we define the ReLU activation. And now we added this method called backward in a new class which we called as softmax loss class, which is the combined softmax and loss class. In the next lecture, what we'll be looking at is that we will be chaining all the classes together. As you can see over here, I've already prepared the title and the notes for the next lecture. So I'll be showing you an entire code where we put different classes together and run the backward propagation through the entire neural network. So all of the hard work which we have put in so far will culminate in the next lecture. If you are with me until this part, you have surpassed 95% of students, I think, because it's very difficult to stick with lectures as we proceed further and further into the topic. So thank you so much. As you can see, I'm not assuming anything. I'm doing everything right from the scratch, which is one of the fundamental philosophies of this lecture series, to show you everything from scratch. I really encourage you to write down these notes which I'm sharing over here so that you see for yourself. And I'll see you in the next lecture.